Good day, ladies and gentlemen. In the last video, we talked about merge sort and all its recursive glory, but we still need to analyze merge sort to determine how fast it runs, and today we are going to learn the tool that gets us there, the Master Theorem. With a name like Master Theorem, it sounds awesome, and it is nifty, but I don't know if it deserves the Master Theorem. But I'll leave that for you to decide. The Master Theorem lets us analyze the runtime of recursive algorithms that have the following form. What this is saying is that our function has two steps, a divide step and a combine step. This first chunk is just us dividing and solving the problem recursively. We are dividing the original problem by b, and then we are calling the recursive function a times. Look at merge sort. If we are not within the base case, we're going to call merge sort 2 times, which is equal to a in our function. And those two calls are going to solve a problem half of the original size. So b is equal to 2. After we call merge sort twice recursively, we're going to combine the two sides together using merge. This is our combine step. Merge takes big O of n time. So in our function here, f of n is equal to big O of n. Great, we have this function. Now what the hell do we do with it? Well, we need to determine which part is going to take longer, the recursive part or the combined part. And to find out how long the recursive part is going to take, we calculate n raised to the power of log base b of a. Once we have this, we just compare it with our combined step. And this works out to 3 scenarios. Scenario 1, n raised to the power of log to the base b of a is greater than f of n. If this is the case, our divide step is the dominant factor in our algorithm, and our runtime is equal to big O of n raised to the power log b of a. Scenario number 2, n raised to the power log b of a is equal to f of n. In this case, our divide step and our combine step take the same amount of time. If this is the case, our runtime is big O of n raised to the power log to the base b of a times log of n. And scenario 3, n raised to the power log to the base b of a is less than f of n, which is to say our combined step takes longer than our recursive step. If this is the case, our function is equal to big O of f of n. And that's it, 3 scenarios, and you really only need to memorize how to calculate how long the recursive step is going to take and scenario number 2. The runtime of cases number 1 and number 3 are really just equivalent to the dominant term of our function. Let's run it on some examples. Here I have the pseudocode for an algorithm that finds a maximum subarray. And I will tell you that this find maximum crossing subarray is equal to big O of n. So our function is equal to 2 because we're calling the recursive step twice, n divided by 2 because we're dividing the problem size in half, plus big O of n. N raised to the power of log base 2 of 2 is equal to n. This is equivalent to our combined step, which is big O of n. So in this case, it is case number 2. And our runtime is equal to big O of n log n. And for this next example, I'm just going to skip the pseudocode and we're going to solve this equation using the Master Theorem. N raised to the power of log to the base b of a, or log to the base 4 of 3, is equal to 0.79. And n log n is greater than n raised to the power of 0.79. This means that our combined step takes more time, and therefore our runtime is equal to n log n. And that's it, that's the Master Theorem. It works fantastically when it does work. There are some technicalities and there are some considerations that you have to keep in mind when you want to use this theorem. They do arise and they can be tricky. The first technicality is with scenario number 1. Not only must f of n be smaller than our recursive part, it must be polynomially smaller. That is, f of n must be asymptotically smaller than our recursive part by a factor of n raised to the power c for some constant c that is greater than 0. And the second technicality is, in the third case, not only must f of n be larger than our recursive part, it must be polynomially larger. So let's look at an example of when a recursive algorithm can fall through this gap. Let's take a look at this function. Upon first glance, it looks like a case of scenario number 3. N log n looks bigger, but it is not polynomially bigger. If we take the ratio of the combined step to the recursive step, we get log of n, which is not bigger than n raised to some power c. So in simpler terms, these limitations mean that the master theorem can only be applied to a specific type of recursive algorithm. If your recursive algorithm doesn't match this pattern of divide and combine, or if f of n doesn't grow in a specific way, then you cannot use the master theorem to analyze the time complexity. Hopefully though, that will not be often, and in my experience, it is not. Most of the time, they're pretty easy to determine, or you can use the master theorem to figure it out. And that's it. That's the end of this video. That's Master Theorem. Let me know in the comments if you think it is deserving of its grandiose name. And stay tuned, because in the next video we are going to talk about heaps. Exciting stuff you're not going to want to miss. Anyways, if you liked the video, like and subscribe. If you did not like the video, dislike and slander me in the comments. Have a fantastic day.